Okay, so here is another dependent motion problem. And I chose this one because it's a little more challenging than the other ones we've done. And for one is, in this case, the collars are moving at different rates. And so that's new for us because normally we have all of the collars, well, they do move at different rates, but it's all dependent on the pulleys. In this case, we're given initially that collar A starts from rest at t equals 0 and moves up and with a constant acceleration of 3.6 inches per second squared. At the same time, collar B is moving downward with a constant velocity of 18 inches per second. So you could see that collar A and B can move independent, and C will kind of equalize what's going on depending on the relative rates of A and B. So we want to determine the time at which the velocity of block C is 0, since C at some point has to be 0 if they're moving in opposite directions, and then the corresponding position of block C when it happens, and that would be a relative to, I believe, their starting position. So let's go ahead. First thing to do is to, of course, draw our position variables and then do our best to draw our actual equations for each of the positions. So go ahead, attempt that, and then I will show you what they should be. So hopefully you got that. I picked the datum to be the center of the pulley, so I have A, B, and C. So now write the equations. Okay, so here are the equations. Hopefully these are what you got. Now we look at everything over here. Now, first one, YB minus YA. So this little piece of string here is what YB minus YA is. And so notice that this whole piece is fixed all along here. So it really doesn't matter that the string is up there because this whole piece constitutes B. So YB minus YA is that little piece. YC minus YA, well, here you can see that, and then you can see YA. So this piece to the far left is that. And then we have our two pieces here, which are just 2YC minus YB. So two of those, okay? Got a little squished in the corner, but that's YC minus YB. And so that equals 0. So if we rearrange those, we get 2YC minus YB minus 2YA is a constant, and then we have our subsequent velocities and accelerations. All right, so now we need to move forward with what we know, and we can use these equations and the information that we're given to then solve. So we're given that the velocity of A initial is 0, right? We know acceleration of A is equal to negative 3.6 inches per second squared. Sorry, so negative 3.6. And we know that the velocity of B initial is 18 inches per second. And the acceleration of B is 0. So if we look at equation 1, all right, and again, you have to kind of look at it and see what makes sense. So if we look at equation 1, we know the velocity of B, we know the velocity of A is 0, so we can figure out what the velocity of C is, can't we? So the initial velocity, of course. So we know VC naught is going to equal, and so if we have VC, we're going to divide it by 3, so it's going to equal 1/3 VB naught plus 2 VA naught. All right, so again, we're looking at the initial velocities. And so if this is VB is 18, so 1/3 of 18 plus 0, well, then that's going to give us a value of 6 inches per second. Okay, hopefully that makes sense. So that's using equation 1 to find out what's going on. So equation 1. Then we're going to also look at the same thing, acceleration c. So because we're trying to figure out the velocity of c and the acceleration c, so that's the way we can figure out when it's not moving. So we have that. So vc naught equals 6 inches per second. Now, let's say we have AC equals the same thing, 1/3 of AB plus 2 times 1/3 AB plus 2 times the acceleration of A, all equals 0. And up here, I just added the brackets, got ahead of myself because I knew this was 0, so it didn't matter, but you need the brackets to distribute the 1/3. So I should have done that up here. But again, with something like this, doesn't change the answer, but better algebraically. So AC equals 1/3. So what do we know? That's going to be AB is 0, right? So that goes away. So we have AA is negative 3.6. So basically we have 1/3 times 2 times negative 3.6, right? So 2/3 of 3.6 or 2/3 of 36 is 24. Therefore, AC equals negative 2.4 inches per second squared. Okay. Now it's just using equation 2. So equation 2 for this. Again, this just dividing all by 3. And so you can see how everything started with getting this correctly. Then we come down here and we have 2/3 of 3.6 or 2.4. All right. So next step now, we have velocity and acceleration. Now we need to develop position and velocity equations using our kinematics, because what we don't have is time. So we can write this now as VC equals VC naught plus AC times time. Nothing new about that. And so VC naught was 6. So we rewrite this as VC equals 6. And then acceleration is AC times T. So go ahead and put in our acceleration of that. So we're going to have a acceleration of C being 3.6. So we'll put that in our equation. VC equals 6. Sorry, I got distracted there. And that's going to be minus 2.4 T. Okay. So go ahead and solve for time. Then we know VC is 0, but before we solve, let's actually get the second equation. I'll explain it. So we have this equation for VC. It's equal to 6 inches per second minus 2.4 inches per second squared times time. So it's slowing down. All right. Then our next equation for position is going to be XC equals XC naught. Now, instead of putting it on that side, I'm going to make it XC minus XC naught, because remember, that's going to be our delta X. Because what does it ask? It asks the corresponding position of the block. Well, we don't really have a 0 point per se. We have a datum, but we're just going to have to say relative to where it started. And so if we're going to assume that it started at 0, then this XC minus XC naught is going to be, we're going to assume this to be 0 here. Okay. That's all you can really do unless you're given specific distance information. So if we go ahead and plug that in, that's going to equal what? Equal the V naught times time. So 6 times T, and then that's going to be plus 1/2 at squared. So we know our acceleration is negative 2.4 and then t squared. Okay. So now we have our two equations. So we can come back up here and solve for t, in which case we solve for our time. So coming back to this time, because again, we want it when VC is 0. Okay. So that goes to 0. So time, if we solve for it, is 2.5 seconds. All right. So 2.5 seconds gives us that. And then we can just plug it in down here. So we get 6 times 2.5 as it's slowing down. And that's going to be plus 1/2 times negative 2.4 times 2.5 squared. And so the total is going to be, when we get over here, is 7.5. That's what this is going to equal. So this plus that is a 7.5. Okay. So our distance, part B, is 7.5 inches moving down, because that's what started. And that started moving down. So remember that collar A was starting at rest, but collar B was moving downward. And so we used, sorry, backing up, collar A was started at rest, collar B was moving downward. We defined those here. We used that to plug into kinematic equations based on this to isolate our acceleration C, velocity of C. Okay. So the end, the math's real easy, but going through the whole, oh, sorry, I didn't know, I thought maybe I stopped recording. I want to make sure I got all that. So in the end, you have just the basic kinematics, but if you didn't set this up correct, you can see how that wouldn't have worked out well, because you had to have this relationship here and this relationship there. So hopefully that helps. A little different problem. I'll try not to stop moving it. There's that. As we slide up, you get the whole thing. So I would encourage you, again, is to try to work this out, write it out, understand each step, and hopefully this will be help you out when we get to this part in a quiz or a test. Thank you.